So in this lecture, we will be discussing how a Markov model is represented mathematically, and by extension in computer code. As you recall, the Markov model is used for modeling sequences. The question is, sequences of what? For the purpose of this section, we will be considering sequences of categorical symbols, which we will simply call states. So for example, if we're modeling the weather, we might have 3 states: sunny, rainy, and cloudy. If we're modeling language, then our states might be parts of speech tags, for example, noun, verb, adjective, and so forth. Okay, so these are examples of states, which are categorical symbols, and by creating a Markov model for these symbols, we will have a model for sequences of these states. In this section, we will use the letter S to mean state. Note that in other resources, you may see other letters being used, such as Z or X, depending on the context. But in this section, we will use the letter S, since that seems to be a neutral symbol. Now, given this letter S, we can use the notation S of t to mean the state at time step t. In this course, time will also be discrete, so we'll have time step 1, time step 2, and so forth. But we won't have something like time step 1.5. Okay, so one convention we will use is that we are going to number the states from 1 up to m, where m is the total number of possible states. So for the example where the states are cloudy, rainy, and sunny, m would be 3. In general, when we want to refer to a specific state, we'll use the letter I or j. So for example, p of s of t equals I translates to the probability that the state at time t is equal to I. Now, of course, we can have such a probability for all values of I from 1 up to m. This gives us m different probabilities, and together, they form a probability distribution. This distribution has a special name. We call it the state distribution. So for example, the state distribution would answer the question, what is the probability that the weather is rainy on Sunday? Note that as shorthand, we may simply write P of S of t to refer to this distribution. Now, as you recall, Markov models are all about modeling sequences, where each state depends only on the previous state we came from. So using mathematical symbols, we can write P of S of t equals j, given S of t minus 1 equals I. So what does this mean? If we translate this into words, it translates to the probability that the state at time t is equal to j, given that the state at time t minus 1 was equal to I. Note that this is a conditional distribution. Now, one question we can consider is this. How many of these conditional probability values exist? Well, we must have a value for every possible I from 1 up to m, and every possible j from 1 up to m. Therefore, we should have m times m values, which is m squared. Now, you may have noticed that it's quite tedious to write down P of S of t equals j, given S of t minus 1 equals I. In fact, we normally avoid writing this. Instead, we can simply store all these values in a matrix called A. We call this the state transition matrix. Our convention is that Aij is equal to the probability that the previous state was I and the next state is j. Thus, the first index corresponds to the previous state, and the second index corresponds to the next state. And clearly, A has the shape m by m. It has m rows and m columns. Now, you might have noticed something weird about our definition of A. If we look closely, we can recognize that in fact, one variable is missing. The variable that's missing is the time t. So what happens to t? So in general, these conditional distributions may change over time. That is to say, they will be functions of t. But for the Markov model, this is usually not the case. Instead, we will assume that the same probabilities hold for all values of t, that is, across all time. When this is true, we say that the Markov process is time homogeneous. For us, this will always be the case. Now, although this will not be very useful for us in terms of applying Markov models, I thought it was worth mentioning since students often like seeing pictures. So one way of representing a Markov model is with a state transition diagram. In this type of picture, we have one circle for each possible value of the states. The arrows represent the probability of transitioning from one state to the next. So for example, the probability of it going from sunny to sunny is 0.8. The probability of going from cloudy to sunny is 0.2. Note that this diagram assumes that the Markov model is time homogeneous, since these probabilities hold no matter what time step we are at. As an exercise, try to figure out what the state transition matrix for this Markov model would be. Now, if all we have is the state transition matrix A, is our picture complete? The answer is no. You see, A only tells us the probability of moving from one state to the next, but every sequence starts somewhere. Each value in A tells us the probability of going from the previous state to the next state. But if we're looking at the very first state in a sequence, there is no previous state. So for a concrete example of this, just think about a sentence, which is a sequence of words. Suppose our sentence is, "The quick brown fox jumps over the lazy dog." The first word in the sentence is "the," and nothing comes before this word. To handle this issue, we need to define another distribution called the initial state distribution. Typically, we use the Greek letter pi to represent this distribution. So pi of I is equal to p of s1 equals I. In this case, we say s of 1 because we're assuming that time 1 is the first time step in the sequence. Note that, since I can take on the values from 1 up to m, pi is a vector of size m. Okay, so let's recap what we've learned so far. We've learned that a Markov model is described by two distributions, the state transition matrix A and the initial state distribution pi. Given these two objects, we can ask some interesting questions. Here are two questions we're going to try to answer in this lecture. The first question is, given A and pi and the sequence s of 1 up to s of t, what is the probability of this sequence? And the second question we're going to answer is very practical. How do we find A and pi in the first place? As usual, because this is machine learning, we'll be given a dataset, and using this dataset, we'll determine some procedure for estimating the best values of A and pi. Okay, so let's start by tackling the first question. Given a sequence of states and a Markov model, which is A and pi, how do we find the probability of that sequence? Luckily, we've already discussed this. In general, we could apply the chain rule of probability, but thanks to the Markov property, this simplifies to the product of state transitions. The difference now is that we will be using our new variables A and pi to represent our answer. It's also important at this point to start thinking about how you would do this in a computer. Inside a computer, A will be a matrix or a 2D array, and pi will be a vector or a 1D array. Thus, you should consider how you would write some code to carry out this computation, multiplying the required components of pi and A, perhaps in some kind of loop. Okay, so the next question we want to answer is, how do we train a Markov model? Now, to fully derive this rigorously takes some work, so for now, we'll only discuss the intuition. But the intuition is very easy to understand. In fact, it requires nothing but counting. So to begin, suppose that we flip a coin a bunch of times, which is a sequence of heads and tails, and we would like to know, what is our best guess for the probability of heads? Well, we all know the answer to this question. It's the number of heads divided by the total number of coin tosses. As you recall, this is a binary distribution, also known as a Bernoulli. But in our case, we can have m greater than 2. For example, each state is a word in the English dictionary. In this case, the answer is similar. Suppose that we've taken all of Wikipedia, and we would like to know, what is our best guess for the probability of seeing the word cat? The answer is the number of times the word cat appears divided by the total number of words in the text. Okay, so how can we apply this principle to estimating A and pi in a Markov model? Let's start with pi since that's a bit simpler. Pi of I is equal to the number of times each sequence started with state I, divided by the total number of sequences in our dataset. Of course, this requires that our dataset consists of multiple sequences to begin with. Otherwise, our estimate would not be very good. Okay, so what about Aij? Our best guess for Aij is the number of times we transition from state I to state j, divided by the total number of times we were in state I. Now, just in case this is a bit confusing, let's think of an example. Suppose that we're working with the English language and each state is a word. We would like to know what is the probability of seeing the word cat following the word the. This is simply the number of times we see the sequence the cat divided by the total number of times we see the word the by itself. Okay, so let's summarize what we've learned in this lecture, since we've covered quite a lot of new content. In this lecture, we learned that using more generic terms, our job is to model a sequence of states. Our Markov model is made up of two objects, the state transition matrix A and the initial state distribution pi. At this point, you know what these probabilities represent. We also learned how to answer two important questions concerning Markov models. The first question we learned to answer is, given a sequence of states and a Markov model, find the probability of that sequence. The second question we learned to answer is, given a dataset of sequences, find the best fitting Markov model, which means find A and pi. Note that, because this is machine learning, we call the process of finding A and pi the learning process or the training process. Now again, it's always useful to think about how you would implement this in computer code. So as an exercise, consider thinking about how you would take a bunch of sentences, like what you would find on Wikipedia or your favorite book, and compute A and pi. In fact, if you really want to test your understanding, you should write the code to actually do this.